recording. We are still on the equilibrium, but now is the equilibrium for other reactions other than just the acid base. Last time we talked about the acid base, and now we are looking at the equilibrium for other and the factors that could affect the equilibrium. One of the factors that could affect the equilibrium, when we have, let's say we have this equilibrium here for a weak acid, because it reaches equilibrium, is the common ion. What is common ion? Common ion is the common ion is like a similar ion or a species that you have in the equilibrium. So if you have either H plus or acetate ion, can affect this equilibrium. This equilibrium can shift to the reactant side if you increase concentration of the acetate ion, or if you increase the concentration of H plus. So either one of these that goes up, then the equilibrium is going to shift to the reactant side. So basically, if you add sodium acetate, is going to increase the concentration of the acetate ion. So in presence of sodium acetate, this equilibrium is going to shift to the reactant side. Concentration of H plus is going to be lowered at the same time. If you have a mixture of weak acid and the salt of the weak acid, can you tell me how would you name that mixture? Is that acid, base, a neutral, a buffer? What would you name that? When you have a mixture of a weak acid and salt of the weak acid, what would you name that? Acid and a weak and the salt of the weak acid and the salt of the weak acid. It's called buffer. So you have a buffer system, which is a mixture of weak acid and the salt of the weak acid. If you have a mixture of that, to calculate the pH, you are using Henderson equation. So when we say like use of Henderson equation, or when can you use the Henderson equation, is when you have a mixture of weak acid and the salt of that weak acid, or if you have a weak base and the salt of that weak base. What is Henderson equation? Henderson equation says pH equals pKa, this is the pKa of the acid, plus the log of conjugate base over concentration of conjugate base over concentration of the acid. You have to memorize this. So basically, a pH equals pKa plus log of concentration of conjugate base over concentration of the weak acid. So when you have a mixture of the weak acid, you have the pKa will be given to you. If you have the concentration for the conjugate base and you have the concentration of the acid, you could find the pH. It can be used for titration, different stages of titration, or it could be used for a given information for a buffer system. Again, a buffer system is a mixture of weak acid and salt of the weak acid. So if you have a formic acid, so this is a weak acid. How do we know it's weak acid? From last chapter or last unit, we had a table that contained a name for 6 strong acids. And any of those, any acid that is not part of the 6 acids, 6 strong acids, is going to be named as weak acid. So we have a weak acid, and then this is the salt of this weak acid. So basically you remove the hydrogen, or if you remove the hydrogen from the acid and add a cation, then you have the salt of the acid. So you see that the similarity. See, this is the conjugate base acid. So you have the acid and the salt of the acid. How do you add the conjugate base? You are going to add in form of a salt. Salt that is based on this acid. So what would be the pH for this solution? A pH for the solution, because we have a mixture of the acid and the salt of the acid, we are using Henderson equation. As long as, so major part of problem solving is understand the problem and memorize the formulas. So pH for strong acid was just negative log of concentration of H+. pH for weak acid was negative log of concentration of H+, but you had to find the concentration of H+ based on the ionization. For the buffer solution, when you have a mixture of the acid and the salt, you end up with this. You are going to use the Henderson equation. You calculate the pH based on pKa and concentration of conjugate base at the equilibrium and the acid at the equilibrium. So you're going to write the ionization for the acid. Then you have your initial concentration. Your initial concentration is given for the acid. If you didn't have the mix of the salt with this acid, this would have been 0. But since you are given initial concentration for the salt, you do have initial concentration for this conjugate base. The changes, again, we are using single variable x, where the concentration is decreasing or the concentration is increasing. We are using the plus and a minus and the plus sign. So concentration, the acid is going to dissociate by variable x. So we have a minus x. At the equilibrium, you would have the initial and affect the change, which is a minus x. So this is the concentration at the equilibrium. When you have the pKa value for the sample for your acid, based on the pKa value, you can actually you can approximate the x value and say the 0.3 minus x is equal to 0.3, and then 0.52 plus x here. If x is a very small number, you can just approximate this also. If the value for Ka is small, then your approximation is going to be, if it's very, very small, your approximation may not be valid, but for this pKa is going to be valid. So first, and it's easier and faster for you to approximate the x. So concentration of the conjugate base at the equilibrium with the approximation is just 0.52. Concentration of the acid at the equilibrium with the approximation is 0.3. You are using Henderson equation to find the pH. When can you use the Henderson equation? When you have a mixture of weak acid and the salt of weak acid. So a buffer solution is a mixture of weak acid and the salt of the weak acid, or a weak base and the salt of that weak base. So both of them must be present. Your acid cannot be a strong acid, and the salt of that acid must be included. So if you have a weak acid of acetic acid, the salt of the acetate is necessary in order to make a buffer solution. So we have an example on the next slide that shows if you have a buffer or not. So that could help you to recognize if you have a buffer or you don't have a buffer. But when you have a buffer, you have the weak acid and you have salt of that weak acid. Is this a buffer or is not buffer? Recognizing a buffer. In order for this system to be buffer, your HF must be a weak acid. And since this is a weak acid, then the first condition is met. So we have a weak acid. What's the second condition? The other piece must be the salt of this weak acid. Is KF salt of HF? Yes, you have the same anion. So this is the salt of the weak acid. So if you have the weak acid and the salt of the weak acid, or the conjugate base of the weak acid mixture together, then your system is going to be a buffer system. So this is a buffer system. So A is a buffer system. What about B? Is B a buffer system? First, you look at the acid, HBr. What's the first condition? Your acid has to be weak acid. Or if it's a base, it has to be a weak base. Is HBr, because it's acid, is it a weak acid? No, HBr is not a weak acid. HBr is one of the 6 strong acids. As soon as the first condition is not met, you don't have to even check the second condition. Even though second condition is true and this is a salt, but it's not the salt of weak acid, it's the salt of strong acid. So it's not buffer because this is a strong acid. For C, we have a base, and is this base a strong base or weak base? How do we know is a strong base or weak base? This is coming from, is it coming from group 1A to a hydroxide? So is it sodium hydroxide, barium hydroxide, lithium hydroxide? Then it's going to be a strong base. If it's not, then it's going to be weak base. So we have the weak base, and then we have the conjugate acid. So we have a weak base and the conjugate acid of that weak base. So if we have a weak base and conjugate acid of the weak base, then we have a buffer system. So we have the carbonate ion as a weak base, and then this is the conjugate acid to the weak base. So we do have a buffer solution. This is just to recognize. Why do we need to recognize? Because if you recognize you have a buffer system, then you would use the pH equals pKa plus log of conjugate base over HA, concentration of the acid and conjugate base. So if you recognize you have a buffer, then you know what formula you should use. So it's going to cut many steps down. Any questions? No questions? Okay. So pH, what is unique about buffer system? A buffer system, it can maintain the pH with limited acid or base added. The pH is not going to change a lot. Like in this example, after we go through the calculation, you see that before adding any acid or base, you have pH 9.17. After adding 20 milliliters of strong acid of sodium hydroxide, the pH, it changed only by 0.03 unit. So this change in unit, this change in pH is very unusual. If you had acid that you're adding base, it would increase the pH a lot because you're adding 20 milliliters of a strong sodium hydroxide base. The pH must have increased a lot. The reason the pH is approximately the same is because the system that you have is a buffer system. And what is the characteristic for buffer system is that is going to maintain the pH. The structure or composition of a buffer system is a weak acid, salt of the weak acid, or conjugate base of that weak acid. Characteristic for it, or unique property for the buffer system, is the ability to maintain the pH. So this example is proving the ability of the buffer system to maintain the pH. You also have a basic buffer that is coming from weak base and the conjugate acid of that weak base. So it has to be mixture of the two. So if we have here, it says calculate the pH of a combination of NH3 and the NH4Cl. We already should recognize that this is a buffer system because we have a weak base and the conjugate acid to this weak base. So we have a buffer system. And if we have a buffer system, we can calculate the pH using Henderson equation. What is Henderson equation? Henderson equation is pH equals pKa. So if we have the Ka for the conjugate acid, we can find the pKa. Just take negative log of the Ka to get the pKa, and then log of concentration of the conjugate base, which is, this is the base, NH3 is the base, and then concentration of the weak acid or conjugate acid. So base over the acid, there's the plus sign here, okay? Base over the acid. So when we recognize that this is a buffer system, we can calculate the pH. Now, the second part of the question is saying, what would be the pH after you add 20 milliliters of sodium hydroxide solution to 80 milliliters of this buffer system? And you would expect the pH to change a lot, but after you do the calculation, you see that the pH is maintained and it doesn't change a lot. How do you find the new pH? Then you have to, still is a buffer system, but first you have to find the concentration of NH3 and concentration of NH4 plus after addition of the sodium hydroxide. So what's going to happen? This is the second part of the problem that you have. So initially, you have the number of moles or moles of the NH4 plus. How do you find the number of moles of NH4 plus? You have the volume, number of moles equals molarity times volume in liter. So if you have the molarity times the volume in liter, you can find the number of moles for NH4 plus to begin with. You have the molarity times volume for the base that you're adding. So concentration at the beginning of the hydroxide ion is going to be, this is how much you're adding. And then concentration or number of moles of the NH3 to begin with, the initial concentration is coming from molarity times volume in liter for NH3. So you would write because you want to use the Ka, right? If you want to use the Ka, you are going to write dissociation of the conjugate acid or hydrolysis of the conjugate acid plus the base that you're adding. The base is going to react with the conjugate acid. If you add acid, it can react with NH3, but since you're adding base, it would react with the acid. So NH4 plus and hydroxide is going to give you H2O and NH3. So this is your chemical equation that it involves concentration of the base and concentration of the acid. Before anything, you would have the concentration calculated or number of moles calculated for each species. And what happens to the change or during the change? You're adding a very strong base, so it's going to react completely until it's finished. So you would 0.001 mole of the sodium hydroxide is added, is going to consume entirely. This is going to consume because it's a strong base and it's going to react with the acid completely until it's finished. And with how much of the acid is going to react with the same number of moles. So if you add 0.001 mole of the hydroxide, is going to react with 0.001 mole of the NH4. So this number of moles of NH4 is going to be consumed. So what you have at the end, so this is the ice again, or very similar term, start, change, and then end. This is initial, change, and then at the equilibrium or at the end. So you end up with lower concentration, slightly lower concentration of the NH4 plus and slightly higher concentration of NH3. But since it's not direct effect, it's based on the log of that ratio, the change is not significant. So you are using Henderson equation again, the Ka, or then as a result, the pKa is going to be the same. But this ratio, instead of being 0.3 over 0.36, you have a 0.25 over 0.28 is the concentration. When you are using number of moles, so basically this is the number of moles that you have here, because you cannot subtract concentration. You have to change it first to number of moles so you can do the subtraction. And then before using the Henderson equation, you have to change the number of moles to the new concentration. Concentration after adding the two solution is going to be calculated based on the new volume. What is new volume? You have 20 milliliters of the buffer and the 80 milliliters of the 20 milliliters of sodium hydroxide, 80 milliliters of the buffer. So 20 plus 80 milliliters, that would be the new volume. And since the new volume is going to be 100 milliliter, you divide by 1000 to change to the to liter, and that is going to be 0.1 liter. So when you have number of moles, you have to change to the new concentration again before you can use it for the Henderson equation. So these are little points that you have to pay attention, because if you use the concentration directly, you may not get the same, you're not going to get the same number. It doesn't fit in this formula. For Henderson equation, you must use your the concentration of the base concentration of the acid. You cannot use the number of moles, so you have to change it. Okay. Now, last time I noticed that the recording was very long. So I'm going to stop recording and start again. So this way you get like multiple recording, smaller units. So this way hopefully is going to be, we just finish with the buffer and then I stop the recording. So I'm going to break into smaller videos instead of 2-hour video. Maintaining the pH, that's the characteristic for a buffer system. So because your blood is a buffer system, if you add acid or base, limited amount of it, the pH is not going to change. The pH of the blood is from 7.35 to 7.45. It has to be the same. It has to be maintained, this number, because if it's lower than this or higher than the higher end, the cells is not going to survive and it will, cause death. So you don't want to, so the pH of the blood is maintained because blood is a buffer system.